This conference will now be recorded.
Well, hello everyone, and welcome to Stamp Chat. My name is Heidi Rhodes. Today on Stamp Chat, we welcome Dr. Frank Corwin. Dr. Corwin is a diagnostic medical physicist in the Department of Radiology at Virginia Commonwealth University. As part of the medical physics graduate program, he teaches the Physics of Diagnostic Imaging course. Frank has been a lifelong stamp collector and has worked postage stamps on diagnostic imaging into his lectures as teaching aids. Dr. Corwin will be marrying his profession and passion in today's presentation, Medical Imaging on Stamps. Today's Stamp Chat is sponsored by the American Philatelic Research Library. If you're an APS member, you're able to borrow materials from the library or request scans, photocopies, or research for all of your philatelic questions. To find out more about the library, visit our webpage at stamplibrary.org and explore all the services we provide to both members and non-members. And now for our presentation. Thank you, Dr. Corwin.
Take it away, huh?
Take it away.
Well, welcome everyone. Good afternoon. This is going to be perhaps a slightly different stamp chat than we've been seeing in the past. So usually we have these really great stamp chats where the presenter is talking about a particular stamp or maybe a development of a particular stamp. We had one on beer revenue stamps. That was great many months ago. What I have here is I actually teach a college graduate level class. It's the Physics of Diagnostic Imaging. And last year I decided I'm going to start adding postage stamps kind of as teaching aids in my lectures. And then once I got through the semester, I had further revelations. Why don't I make this talk into a presentation for my local stamp club here in Richmond? So I was doing that and I had it all done. And there was a stamp chat I was listening to one day. Dr. David Strittmatter was talking about using postage stamps in the college classroom. This is great, and he had some wonderful ideas, and I happened to ask him a question and tell him what I was doing, and immediately Heidi pounced. Said, Frank, you're doing a stamp chat for us. So I wouldn't have ventured if I didn't want to do it, but here I am. So I hope you all enjoy this. So this is going through diagnostic medical imaging. We're going to go through a semester-long course here in about 45 minutes, and how postage stamps can be incorporated into that, and to understand the physics and then the imaging modalities. So moving ahead, which I hope will work, there we go. This is a standard slide right out of my presentation, just to give my students kind of an idea of who I am. I've been here at VCU, probably, we used to do research on the dinosaurs back in the early days. I've been around quite a while. I've done mostly MRI research, and I've moved into diagnostic physics work. I actually came up through the same program that the students are in. So they started this program back in the early 2000s, and I just jumped in right away and got my PhD through it. And I've been a stamp collector. I'm a member of the Greater Richmond Stamp Club. And when I was telling our president that I was presenting this, he was saying, I'm glad you're presenting this for an international audience before you give it to us. So this is my practice run, and you all are the guinea pigs. Well, Heidi asked me a great question a week or so ago. She says, what's a medical physicist? Okay, so I threw that in. Medical physicists are physicists who specialize in the concepts of physics and how they relate to the diagnosis and treatment of human disease. We don't offer a diagnosis. If you have a broken bone, I'm not going to tell you your bone is broken. That's not my field. Nor am I going to offer a treatment, take 2 aspirin and call me tomorrow. That's out of my field. Our concern is, what does the image quality look like? Is the doctor who's going to be diagnosing you, does he have the best image quality possible? And as you as the patient laying on a table getting a dose of radiation, are you getting the lowest amount of radiation possible? So that's kind of how the medical physics comes. Make sure you get low dose and the doctor gets great images. And then we try to balance those two. That's what a medical physicist spends their life doing. A diagnostic imaging modalities. I'm sure everyone on this webinar has probably been touched at some point by one of these. You could have there's various ways to have an imaging done in the Department of Radiology. So in physics here, there's really 2 big areas. There's the diagnostic world and the therapy world. I'm only going to be dealing with the diagnostic world, which is what you would come to in radiology. So you could have an X-ray based study here, an X-ray tube, or perhaps a nuclear medicine based study where they actually inject radioisotopes into you, or an MRI study where it's using radio wave energy to excite the nuclei. or ultrasound. So in my class, I'm teaching the X-ray based and the ultrasound. And in this talk, I'm only going to cover the X-ray based because there's so many stamps and all the others, it would take many hours. So we'll be talking the X-ray based physics here and the imaging modalities. We'll go through some absorption scattering properties, talk just briefly about the detectors, and show some images, a lot of the images that come up on postage stamps. Let's dive right in. So what is X-ray imaging? What is X-rays, first of all? So X-rays are a form of electromagnetic radiation. It's characterized by wavelengths and frequency and energy. Visible light that we see around us all the time is just a tiny sliver of that EMR spectrum. And here at the bottom, you can see what a spectrum looks like. And there's this beautiful stamp from Germany showing a spectrum of light. This was done by Josef Fraunhofer, where he actually measured some absorption bands in the solar spectrum. And I'll talk a little bit about how that can happen later. But it's just a nice color image going across the whole spectrum. To be able to make an image with this electromagnetic radiation, this radiation has to both be able to transverse a thickness of matter, maybe tissue in our case, and it's got to be able to interact with that matter. So it's got to do both at the same time. So it has to have a wave property and has to have a particle property. The wave to be able to transverse the tissue and the particle nature to be able to interact. And that's Planck and actually Einstein together came up with the physics behind how this works, and it's described in the Planck equation. A couple of nice postage stamps, Max Planck. A beautiful stamp here giving the Planck equation, also from Germany. And I love this one here at the bottom from East Germany, which gives the Planck's constant, 6.62 times 10 to the minus 34 joules per second. So they actually just gave you the constant. H is a standard physics constant. If you see an H in the equation, we know that's Planck's constant. Once you've generated the electromagnetic radiation, it has to interact. So we have to understand what is going on at the atomic level that causes this interaction. And there's a beautiful history behind this. Some of the probably the earliest concept of matter was by Democritus, who said that all matter is made up of some type of primary matter arranged in different sizes and shapes, and he called that atoms. So we have this concept of atoms going back 2,000 plus years. Thomson came along and he proposed that atoms must be some sort of glob where you've got positive and negative charges kind of mushed together. It was called a plum pudding model. So if you imagine a plum pudding, it's a nice pasty mix, and then you got these plums in there. You stick your finger in it, you can pull out a plum. So that was his concept, that the positive charges were just kind of the plums in this mix. Good initial start, not quite right. Rutherford came along. He was the next physicist in line here. He expanded this model through observations that the atom must contain some sort of tiny point source positive charged nucleus. He did this through an experiment which we refer to now routinely as the Rutherford scattering experiment, where he bombarded atoms with alpha particles. The alpha particles have a positive charge, and the nucleus of an atom has a positive charge. So when these positive and positive came together, one would be repelled by the other. The New Zealand stamp here shows it very nicely. You can see the large dot in the middle, that would be a nucleus. And these arrows would represent some sort of positive charge, an alpha particle, approaching that nucleus and then being deflected as they get closer. Kind of like pushing two north ends of a magnet together. They want to push apart. And this Russian stamp here also, beautiful explanation. It shows you the actual angle that's how that positive charge would veer away from that positive nucleus. And there's a nice equation, the Rutherford scattering equation. This angle is determined by a cotangent variable. It's one of the classic equations that the physicists will learn how to develop in their dosimetry course. Not in my course, but in one of the other more math-based courses. Niels Bohr, also a renowned physicist. He took this theory one step further and decided that we do have a positive nucleus, but the electrons are not just in some kind of glob around this nucleus. They must be in some sort of defined orbits. It's a very simple way to think about it. We can think about it kind of as a planetary model, where the orbits are in defined distances from that nucleus. And because of that, they have some sort of defined energy. We have a couple of stamps here from Bohr. There's actually a whole bunch of them out there. And I just picked some here in particular. I'm being disturbed here from outside my office, so excuse me a second. Bohr showed that these electron orbits, they have a defined energy level. It's a quantized energy level. So an example here from a tungsten atom, the K shell, which is the one closest to the nucleus, has a defined energy level of 69,500 electron volts. As you go further out, those electrons are held in with slightly less energy. Okay. Part of Bohr's experiment was he would irradiate atoms. His irradiation, which could have been X-rays or it could have been electrons or something, would knock electrons out of these orbits. And nature of Bohr is a vacuum. So as soon as you knock something out of one of those orbits, something else falls in, another electron from somewhere else. It could fall in from one of the other shells, or it could fall in from the valence shell, or it could even fall in from the valence level way outside. But to fall in like that, that electron has got to give up energy. So an example here, if this 2.5 keV, this electron, whoops, out here, I knew I would do that eventually. This electron out here that's held in at 2.5 keV, dropped down to the minus 65 keV, it's got to give off energy. So 69.5 minus 2.5 means it's giving off a 67 kiloelectron volt characteristic X-ray. And here's a nice stamp from Denmark that actually described this equation. The energy of the photon that's emitted is equal to the change in the energy of that electron from its original state to its new state. And if we stuck in minus 2.5, minus 69.5 here, we'd end up with a 67 kiloelectron volt characteristic X-ray. I'm not going to go into this too much. This was just a pretty slide I put together. So once you had the basic understanding of atomic structure, then physicists ran everywhere and developed wave equations and understanding how the electrons work. And Sweden came up with this really beautiful set of stamps on quantum mechanics and various postal and non-postal stamps here of the different physicists. So if you've earned a Nobel Prize, you pretty much have a postage stamp out there. But the main things I want to cover was just that transition in energy, which becomes very important then when we get into our diagnostic imaging. Let's go back to X-rays now. So we talked about here how some radiation is created. Let's go into the history of radiation. One of the first devices that was used to create X-rays was the Crookes tube. William Crook was actually working with a predecessor type tube, so he improved it, and his improvement was known as the Crookes tube. He would put a high voltage between this cathode end here and an anode end. Let's see, my mouse is going to show over here. Okay. So the cathode end here, hopefully my mouse is showing, and the anode end here. So you're going from a positive voltage, a negative voltage, I mean, to a positive voltage. So electrons are flowing from here. They're being pushed off by the negative voltage and attracted to the positive voltage on this anode. In a Crookes tube, you've got some residual gas inside of there. So it's kind of like a neon tube. It's a little bit messier than that, but you'll see a beam of these electrons interacting with the gas in the Crookes tube and causing a glow. And then as it hits the end of the tube, you have a nice glow there, and you'll get a shadow from whatever your anode is. Here it's a Maltese cross, which is what they were using at the time. Unfortunately, there's no stamps for Sir William Crookes. He never earned a Nobel Prize. He was a great scientist. He discovered, and he was quite renowned, but he got involved with some paranormal activities and trying to do research on that, and it kind of tarred his reputation. So he never earned a Nobel Prize for the work he was doing. William Röntgen, of course, is the big guy. He's the one who was doing some experiments with a Crookes tube when he discovered some sort of new radiation. So he took his Crookes tube, he powered it up, then he put it in a heavy cardboard box. He had a fluorescent screen sitting off to the side. Fluorescent screen is something like barium platinum cyanide material. It will glow when it's hit by X-ray radiation. So he had known about this. He had his tube up and the plate, it would glow. Now he put the Crookes tube in a box and the plate still glowed. So how was whatever coming out of this tube getting through the cardboard out to there, out to his screen? And he called this, and figured out, oh, I've discovered a new radiation. He called it Xstrahlen. Within a couple of days, he used an actual photographic plate and took a picture of his wife's hand. So this is the first X-ray image of Bertha Röntgen's hand. And that's shown very nicely here on this stamp from Mexico, where they incorporated. And this Monaco stamp shows Röntgen's with a Crookes tube and the X-ray image that could be created with the Crookes tube and the radiation, the X-rays that it made. Röntgen immediately became an international superstar. So all those physicists I went through, Röntgen was really the predecessor of everybody. His discovery of X-rays opened up the whole field of quantum mechanics and nuclear physics. So if you wanted to do a thematic study on Röntgen, you probably could find 50 stamps or more on him. The earliest one, I believe, is probably this one from Freistadt Danzig, which came out in the late 30s. And then there were many, many more that followed that. Some real stamps and a bunch non-postals, Guinea-Bissau and some Malis that you probably won't find on envelopes anywhere. X-ray tubes pretty much expanded rapidly after that. The Crookes tube was very inefficient. It was only moderately evacuated. It was like the neon tube I was talking about. So there was a lot of ionization and collisional energy loss. So the X-ray radiation you created was really a mess. It's not very well defined. They used what's called a cold cathode. So electrons had to be pulled from that cathode to travel to the anode. It's a little bit more difficult, so it's a very inefficient design. In 1925, Coolidge improved the tube design. We call it the Coolidge tube, actually. So he stuck in a very high vacuum, simple to do. He heated the cathode. By heating the cathode now, you're giving those electrons a little bit more energy, so you're boiling them off of the cathode. And now that they're off the cathode, they have a much easier chance of traveling to the anode, where they'll hit the anode and create radiation. And he also shaped the cathode too, something new. In the Crookes tube, the cathode was just a flat piece of metal. In Coolidge tube, it was shaped, and I have a slide coming up that I can show you that. Here's some stamps basically showing a Crookes tube, and this one here from Finland shows a Coolidge tube. Has a higher vacuum. You can see, kind of make out perhaps there's a shaped cathode in this, and then some sort of anode here with X-rays coming out of it. Modern tubes, we've really come a long way since those early tubes, of course. They now have, so instead of having some sort of flat piece of metal that works as the cathode, we're generally using a wire that's inside of a little cup. And the cup is a focusing cup, so you're focusing that beam of electrons that you boiled off of that wire, and then it can travel over to the anode, where it hits at a certain spot that we call the focal spot. Where that beam of electrons hit on the anode generates a whole lot of heat. An X-ray tube has about 1% efficiency, so 99% of the energy of those electrons just goes into heating the material. And if you're not careful, you'll melt your anode. So modern tubes now have rotating anodes. You can see here in this one picture, this would be the cathode right here. It's a cup, there's a wire inside of that. Here's an anode. This anode is spinning, so that kind of distributes the heat load all the way around that disc, gives it a couple milliseconds before the same point is reached again. Same stamp, same design over here on a stamp by Spain, shows a modern tube. There's a rotating anode. Röntgen would never have seen one of these, so putting the two together is interesting. And this is for the European Congress of Radiology that met in '67. What happens inside that X-ray tube? I've been alluding to it a little bit here. So we have this heated tungsten filament element that's inside of that focusing cup. It's boiling off electrons. because you've got tens of thousands to 100,000 volts between the cathode and the anode, those electrons get pulled towards the anode. The anode's a positive charge. With a focusing cup, they're focused to a tiny point, usually about 1 to 2 millimeters square. And they hit this anode and they interact in that material and they generate X-rays. And I'll get into that interaction here shortly. Here's a stamp from Macedonia. This shows kind of the design of the Coolidge tube with the shaped cathode. And they don't show the electrons, but this would be the X-rays that are emanating from some focal spot point on the anode. What happens in that target now, in that anode? Those charged particles, those electrons, they hit the surface and they're going to interact with the material that makes up that target. They're going to do one of two things. The electrons are going to knock electrons out of orbits on some of the atoms, or the electrons, having a negative charge, are going to interact with this big positive ball of the nucleus. So there's going to be some sort of attraction, and their path of travel will change. As the path changes, they have to give off energy, and that becomes what we call Bremsstrahlung radiation. Stepping back here, as you knock electrons out, I talked about this earlier when talking about Bohr, you've created a hole in that atomic structure around that atom. Well, nature abhors a vacuum, so something's going to drop in there right away, and as it drops in, it's going to give off energy. And you'll end up, this is probably TMI, but the waveform, the energy of the X-rays coming out of the tube will end up looking something like this. A would be your Bremsstrahlung energy, depending how close those electrons pass by the nucleus. So you have a whole bunch of them passing a long ways away, just a tiny amount of them passing real close and giving off all their energy. Right at the surface of the anode, your X-ray beam might look like this, have some sort of waveform like this with energy. But we're doing a lot of filtering because the stuff down here at the low energy, 20 keV and below, is just junk. It's just going to give you dose, and we don't want that, so we stick in some filters to try and get rid of it. So what's coming out of the X-ray tube that'll actually be hitting you laying on the table probably looks something like this. You've got some maximum, you've got some characteristics here from those electrons that were knocked out and new ones falling into those orbitals. And then you've got your Bremsstrahlung that's been attenuated out. We know what happens in the tube. Now what happens inside of you? Also fun. There's 3 interactions that happen inside of you. There's Rayleigh scattering, there's photoelectric effect, and there's Compton scattering. So the X-ray photons, now we're thinking of them as a particle, are going to interact with the atoms in your body through one of these effects. And of course, there's stamps that honor the people that came up with these concepts. Rayleigh scattering. It's named after Lord Rayleigh, John William Strutt. Pretty simple. It involves an X-ray photon interacting with an atom. So it's going to interact with a whole electron cloud, and it really just puts the atom into kind of an excited state where it's perhaps wobbling. And then the photon is re-emitted. It's re-emitted in another direction. There's no change in energy, it's just the photon comes in, excites the atom, re-emitted. And we see this a lot at some of the lower energy interactions. The one that we really like is the photoelectric effect. Einstein came up with this idea back when he was working with Planck on the Planck equation. It's the concept again that EMR has a particle nature. It's this little packet of energy. So when that packet of energy hits an electron, it transfers its energy to that electron. So the photon, the X-ray photon, completely disappears, and the electron has absorbed all the energy and can then be kicked out of the system. Einstein theorized this, that it would happen with metal, and he actually demonstrated that way using just regular light. Nice German stamp here that shows this. Light onto a metal plate. Metal has lots of valence electrons, lots of free low energy electrons. So light, which is a low energy, can easily knock those electrons out. And he was able to record this, and his theory was proven correct. And there's a zillion stamps on Einstein. If you want to do a thematic study here, you could probably find 400 plus stamps on Einstein. Actually, through one of my organizations, one gentleman has compiled a full list of them, and he has about 400 plus in the document that he describes, that he distributes. Actually, he sells it, but still, it's a very good document. In our X-ray energy range, so Einstein demonstrated this with light. Light is low energy. When you get to X-rays, you're dealing with high energy. So the electrons, the photons, I mean, having much higher energy, can interact with the electrons in an atom that have much higher energy. It's an example of an iodine atom. I'll bring my mouse over here. An iodine atom. So you've got some photon coming in. If it has greater than 33 kiloelectron volts, it can knock this electron out of orbit. So if it's 34, it'll knock that electron out. If it's 30, it's not going to knock that electron out. It doesn't have enough energy. So as long as it's greater than that binding energy, it'll knock it out. And then, of course, like I described earlier, nature abhors a vacuum. Something will drop in there. And that atom will then emit some radiation. That electron will emit some radiation. And depending where that electron drops from again, will depend on what the radiation energy is. Beautiful stamp here from Einstein showing his this actual equation. So the energy of our photon, HV, has to equal to at least the binding energy of that electron plus whatever additional energy the electron has. So this photon was, say, 40 kiloelectron volts in energy. It would hit this 33 guy, and this electron would have 7 kiloelectron volts of electricity, 7 electron kilovolts to travel of potential energy that it can then dissipate in the medium. So another great study is stamps with equations on them. This is a very fun project. The final interaction is the Compton scattering. So this is the one that happens probably most of all, and it's the one that we like the least. Here the X-ray photon comes in and will knock out one of the valence shells, one of the lower energy shell electrons. So it'll hit this guy, give it that electron a little bit of energy, but yet you still have a photon that's got high energy left over. So it can go off and hit another electron, knock out, do some more Compton scattering, or worse yet, it can leave the system. Notice it's not going in the same line that it originally came in. There's an angle of deflection, and it can go down and hit the image receptor. And since it's not coming in a straight line, it's going to go somewhere else, and it's going to cause fog on your film. So it's going to reduce your image quality. It's a fact of nature. There's not much we can do about it. We can have various grids and filters to try and reduce that effect some, but it's just an interaction that we have to deal with. And then, of course, there's Arthur H. Compton. He has a stamp from Guyana. Let's get into the modalities. So right now we've gone through about the first month of lectures. The rest go pretty quickly, actually. I spend most of the whole time going through the different modalities, but we do cover the basics of physics in the first couple of weeks, first month or so. So let's talk about some of the modalities here. We have 4 that I will be presenting. There's radiography, mammography, fluoroscopy, and computed tomography. In these, there are, you can mix and match these. There's actually a CT-based mammography, and there is a cone beam CT-based fluoroscopy. You can do fluoroscopy on CT units. So the lines are gray, but these are the 4 big categories. Radiography is where we'll start, often called projection radiography. In the projection radiography, you're transmitting X-rays through the patient. So the image ends up being a 2D representation, just a picture of a 3D object. So you can imagine that if you have overlying tissue, everything is kind of compressed into that 2D image. Beautiful stamps here from Zambia and Uganda that show a basic setup for projection radiography. Patients laying on the table, there's some image receptor underneath them, and the X-rays pass through the patient to the image receptor. This one here from Uganda was issued on their Independence Day, 1962. And last month, we had a speaker, Richard Morrill, was talking about the Tanganyika 1961 Independence Day issues. And he was going through the many variations they went through to finally pick the stamp that was correct. And I wonder if the same type story would apply with this stamp here, that there were many variations. I think it's great that they picked a radiography stamp as their Independence Day stamp. So what happens here? The X-rays leave the X-ray tube. You come over here to this picture. They will pass through air. They go through the patient. They can do one of three different things. They can just pass straight through, like X-ray photon C, down to this image receptor. They could be absorbed, like this X-ray photon here, B. It enters the patient and stops. It's transferred its energy to an electron. That photon stops. Or it could be scattered with a Compton scattering type method I showed you. So it could go in, it could exit the patient, or worse yet, over here like D, it comes in, has Compton scattering, and then hits the film somewhere else, causing some sort of background fog. That's where we have grids that prevent some of that from happening. So the image, the X-rays that make it through the patient, they interact with an image receptor to create a final image. And here we have some really nice stamps. I like this Ghana one where it shows the radiologist looking at the X-ray image as placed up on a view box. Our image receptors used to be film screen. For probably 100+ years, we were using film screen. I'm sure many of you have seen your X-ray films before. It comes on a piece of this cellulite paper, a cellulite screen. You can look through it. If you put it on a view box, which is a really bright box, the light shines through it and can show you the images. Currently, we're pretty much moving everything over to digital detectors. So I don't have any stamps on that. There are no stamps out there yet on digital detectors, but images are acquired on a digital plate. They're immediately digitized, sent to a computer, and then read on workstation monitors. The images that you see here are negative images. So this is if you look at this one here from Ghana, back over to the screen, this is an image of the chest going through the lungs. The lungs are big air-filled cavities. So they're not going to attenuate many X-rays. Because of that, a lot of X-rays get through, and you end up with black is where the X-rays have come through. Your spine and sternum are dense, so they're not going to allow many X-rays through. They're going to absorb more. That ends up being white in the X-ray image. That's what we're seeing here. So it's a negative image. You see that there. You see that somewhat in this picture here from Hungary, and you see it a little bit in the Belgium one, but it stands out very nicely here in the Ghana stamp, where the radiologist is interpreting that. There are many stamps dealing with radiography and public health. Back in the tuberculosis era, 50s and stuff, where they were really encouraging screening for TB. There were mobile units traveling around, going to schools and various places. A lot of countries issued stamps for that, showing usually the truck where they would have the mobile X-ray going site to site. I really like this Korean one here. And I just discovered this Vietnam one recently. It shows the X-ray tube here on the end. It's got the cables to go for the cathode and the anode. And you can see the detector stand in front of this gentleman. Okay, so that was projection radiography. Let's jump over to mammography. Mammography is really projection radiography customized for breast imaging. It's a frontline screening methodology for breast cancer. There's lots of stamps for mammography. Everybody loves their mother, so there's lots of stamps everywhere. This US one here, this is a semi-postal. I think it's our first semi-postal stamp. It was issued in 1998, and I actually just bought some here back in May, so they're still being issued. They were supposed to go off, be discontinued last December, but they're still around now, and I use them all the time. This Macedonia stamp here, I really like this one. It shows an early mammography unit. So originally, mammography was just done on a regular diagnostic X-ray machine. They would modify the parameters, try and do imaging as well as possible. They would use industrial strength film, and not the regular imaging film because it had higher resolution. And CGR came out with a unit. CGR was a French company, They developed this Senograph unit back in the late 80s. GE bought them out in the 90s, so this is probably a GE modified unit then. But it's specifically designed, it's the first unit specifically designed now for just breast imaging. When we're doing projection radiography, earlier we were showing images of the lungs. You know, it's high contrast, they're bone against airspace. If you want to find a broken bone on the leg, you know, bone has high density, has high attenuation. It's easy to see on projection radiography. In mammography, we're looking at the difference between two different soft tissues. Cancer is its own soft tissue and has a slightly different density than does normal tissue. So that's what the mammographer is looking for. And there's various anatomical characteristics that are, it's the microcalcifications that are tinier than a human hair that they have to be able to see. So you can excuse me here for pulling out graphs. Physicists love graphs. If you see here at the low energy range, this is the energy of the X-ray photon. When we get down to these low energy ranges, you actually get some separation between glandular tissue, which would be the white stuff here in this image, and a cancer. So there is a slight density difference in the tissue. That's what the mammographer is looking for. So in mammography, we want the low energy X-ray tubes. It's very important. Screening mammography is usually done in two separate views, a cranial caudal and a medial lateral. So cranial caudal is just a straight up and down tube exposure. Medial lateral is about a 45-degree exposure, and that's what you're seeing in these two images here. And you can see this is a very dense breast, so you're seeing lots of glandular tissue here. Now imagine that there was a cancer in there that had to be found. It's almost the same density. At this point now you're looking for other anatomical structures. This stamp here from Croatia shows an X-ray beam coming in the lateral plane. So a lateral plane might be used if you're doing an actual diagnosis. Something had been spotted on the screening, let's do some more follow-up imaging. Because mammography has such high imaging requirements, you know, the contrast has to be great. We're running special low energy X-ray tubes. We're using special filters. That's what makes mammography really cool, is the filters that we use both for the anode and for as the X-ray beam comes out of the X-ray tube to try and shape the beam so that we get rid of that really low energy stuff that's wasted because it's just absorbed, and get rid of that high energy stuff because it just causes Compton scattering and reduces our contrast. We compress the tissue. You know, the thinner the tissue is, the less Compton scattering you'll have. I know that's not a pleasant thought for the ladies in the audience. You're using incredibly high resolution detectors. And of course, to see that data, you got to display it on a very high resolution monitor. Mammography is really a team effort. I like this Pakistan stamp here that talks about it being a team effort. Your mammographer, your technologist, your physicist all have to work closely together to ensure that the image quality is great. I threw this monitor in here. We actually reviewed some of these here at my hospital. They're about 25 grand each. They're beautiful, but we needed 8, so they're on hold for the time being. I mentioned compression. That's, you know, compression is there to reduce the thickness of the tissue so that you have less Compton scattering. The less Compton scattering, the less loss of contrast you have. Unpleasant as that may be, I go to a lot of mammo sites, and I often see this cartoon posted somewhere in just about every site I go to. You know, a little levity always helps ease the fear. Your women ran the world. Fluoroscopy, our next imaging modality. So projection radiography will give you a snapshot of what's going on. Snapshots sometimes aren't the best thing to see. You actually want to see the anatomy functioning. You might want to see how solids are being processed as they go into the stomach, or as they come out of the stomach, or even beyond that. You might want to see what's happening in the vasculature around the heart or in the brain. Maybe there's an aneurysm in the brain that we need to see. So we need some live imaging. That's what fluoroscopy is. Same principle as radiography, but now the X-ray tube is always on, or at least as long as the radiologist has their foot on the pedal. But it's at a very low energy, so a low output. Here we're just acquiring real-time data. And little picture here just shows that the X-rays come from a tube, pass through the patient, enter this thing called an image intensifier, which enhances the image quite a bit, and goes to various cameras and then out to a monitor. There's a stamp from Germany back in the 1970s of a Siemens serograph. So here you had your X-ray tube up top. Generally, the X-ray tubes are below the table, but this unit here was an up top over the table tube. And your image intensifier would have been below the table down here. Image intensifiers have not always been around, you know, those bottle things up here. And they're actually being phased out now. But in the era before they existed, probably back in the 50s into the 60s, the doctors would have to look at a fluorescent screen directly. So I actually had, when I first started this, I had a machine, I was checking a machine that was a fluorescent screen. It didn't have the image intensifier, and it was really hard to see because they're not very bright, and the doctors would have to dark adapt their vision to be able to see it. So if a doctor back in the 50s, 40s had a fluoroscopy exam, they would either have to go sit in a darkened room for about 20 or 30 minutes, or they could wear, you know, dark red glasses or something just to really get their eyes dark adapted. You can see that on this Qatar stamp. Here the doctor is looking at a fluorescent screen. The room is ideally very dark, so the stamp kind of masks that concept of being so white, but it's done in a dark room so he can actually see the screen. This hungry stamp, I love this one. This is probably my favorite stamp. I'm trying to find a copy of this. This one here shows a doctor, probably this stamp is from 1952, I believe. Shows a doctor looking at a patient as the X-ray beam comes through him and hits a fluorescent screen. Okay, straightforward enough. But what's funny is the doctor is still wearing his dark glasses. I believe what I'm seeing there are the dark glasses he's wearing, where there's the band that goes around his head to dark adapt his eyes, which of course now makes no sense at all. Why would you continue to wear those glasses when you're trying to see something that's already very dim? So I just think this is a very interesting stamp because of that. And this one's definitely in my lectures. I was actually reading an article in the Hungarian Philatelic. It's one of the clubs recognized by APS, and they were having a very hard time with this stamp. It says, translated roughly, socialism is all about the human being. But it was printed during the time of the Hungarian reforms, where there were gulags and people disappearing. So they weren't too pleased with that concept. Modern fluoroscopy, we're actually leaving the era now of image intensifiers. So we're going back to more of a flat panel here, but there's a digital detector inside of these guys. So they're directly converting the X-ray radiation to digital data, which is then fed out to monitors. So a table unit might look something like this now, or the very sophisticated angiography tables, something like this here, where the table can actually float. The table can move in X, Y, and Z, it can rotate, it can tilt, and of course the X-ray tube can swing around and move in all different planes for very complex imaging. We're using these type of machines for work on the heart, work on the brain, thrombosis down the legs, many different procedures. And these are very advanced machines. We're getting a couple new ones here at the hospital. And as us physicists, we get to play with them first because we have to do the acceptance testing. We're asking for about 4 days on any one of these machines because they're so complex now with their different functions that they can do. They're a lot of fun. This here perhaps is more medicine, but it does give an idea of what this modern fluoroscopy stuff can do. So here we have a cerebral angiography image. So a dye, probably an iodine dye, was injected into their carotid artery somewhere in the brain, on the neck, and it goes into the brain, and you can see the vasculature in the brain now. And probably what they're looking for here is some sort of aneurysm, which looks like a bubble, a balloon sticking out on the side, or some blockage or something in the brain. Ergas Moniz was the gentleman who pioneered this whole procedure for cerebral angiography. Likewise here for cardiac study, we can inject an iodine or some contrast agent, some agent that absorbs X-rays more than the surrounding tissue into the heart. and you can see the vasculature of the heart, and you could look for blockages and stuff. I love this German stamp here from Werner Vossmann, honoring Werner Vossmann. He was the first guy that actually did a cardiac catheterization, and to save his nurse, he did this on himself. So he put a cut in his arm, ran the catheter up his arm, followed it down into the heart, and this little orange box here is actually an image. So once he got it in place, he went down to radiology and they took a picture of it, and this orange box is actually that image. I have a picture of it here. So this was in the 1920s, and then he won a Nobel Prize for this in the late 50s. Now, this cerebral angiography and cardiac caths are pretty much run-of-the-mill in hospitals. We have cases going all day. So as a physicist, I want to get in and play with one of the rooms. They'll tell me, sure, we're free after 2 a.m. So you take it when you can. Sometimes they'll give it to me during the day, but and our last modality, computed tomography. So we've done projections, we've done fluoroscopy. Now we want to look at perhaps more detail in an image. So computed tomography, you can think of it basically as a projection image, but you acquire about 1,000 projection images as the X-ray tube rotates around the patient. So it's at every couple of milliseconds, it's like snapping a picture, and it rotates a little bit, snaps a picture. It's actually snapping pictures while it's rotating. It's not a step and shoot. So the tube is spinning and collecting data the whole time. That data is then reprocessed. It's all electronic, and you can generate images from that. So in CT, your detector is probably about 1 meter long, but it's only a couple of centimeters wide. So the beauty of that is now, you remember I've talked Compton scattering is the bad thing in diagnostic imaging. Because our detector is so narrow, you have very little Compton scattering. So our contrast is greatly improved in CT images. Historically, CT came up in the 60s. It really started going to the hospitals in the 70s. Nice stamp here from South Africa, yes. Alan Cormack and the work he did, and Gottfried Hansfeld, the work he did in 67. He actually came up with the first type proto unit. This is just a slide right out of my lectures. You know, CT units first entered in the 70s. It would take about 2 to 3 minutes to get an image back in those days. Some of the first units were cable driven. So because your tube is going around the patient, you somehow have to get the power to it and get the data out of it. The first ones had wires. So you could do 1 revolution, catch images, rewind, do another revolution, collect the images, rewind. Modern units now have something we call slip rings, where the power and the data is actually transferred between fingers and rings on the gantry itself. So this whole gantry can be spinning continuously. And some of our modern units can spin at 3 to 4 revolutions per second. It's like a propeller going around. It's almost scary if you're there in the room with the covers off of it. Hong Kong and Malaysia came out with stamps depicting CT. So this one in Hong Kong's 87. That's probably a GE unit from those days. This year, I'm guessing, looks like a Toshiba unit from 1995. I've worked on some of these. And this here is a GE unit now. Some units on the market have actually 2 X-ray tubes and 2 hole detector systems on the same gantry. You know, the gantry alone weighs many thousands of pounds, and this thing's spinning around with the generators, with the cooling system. It's quite impressive. You know, and a unit now can get 200 images in 1 revolution. Perhaps some of you have had some studies done. I know I had a cardiac scanning once. I was on the table about 2 seconds. It took them 10 minutes to get me set up, but the whole acquisition took 2 seconds. So it's the speed of these guys is really immense. And unfortunately, CT, because it is so versatile, gives such good image quality, the overall dose load to the patient population has gone up because of that. So that's something we really watch out for a lot. And CT manufacturers have really responded with some novel methodologies for controlling the dose that patients get. And the data from CT is fully digital, so you can manipulate it however you want. And I say you slice and dice it. You can create axial scans. You could reformat it into coronal. You could reformat it into sagittal. You could throw on different filters and make the image look completely different. So it's a wonderful tool to have. And I see I am getting close to the end. So my final exam for the class, I even throw a stamp question on it. And I'll see who here might know this answer. So I showed you this stamp earlier. Perhaps it's a little bit easier now. Who's pictured on this postage stamp from Guinea-Bissau? It's a non-postal stamp, but it works. Guinea-Bissau. If you read the stamp, who does it say there? Does that look like old Wilhelm? You know, just to help ease things up a little bit, on page 1 of my exam, I put this stamp, which is, if you read the fine print, Mr. Röntgen himself. And what does Röntgen have? A big beard. Does this guy have a beard? So, well, that's probably not Röntgen, even though the stamp says so. So you go through the list, scratch off Röntgen. Maybe you want to put Dr. Corwin down, but you can scratch that one off too. I've had some people think it was a young Albert Einstein. So it's not a young Albert Einstein. It's got to be Gottfried Hansfeld. So any of my students that are online, this will be an easy 2 points for you come the final exam that we'll have in December. Any questions?
That was fabulous, Dr. Corwin. Wow.
Is it worth presenting to my stamp club now? I see Doug's there. He can shake his head or.
Yes, it's definitely worthwhile presenting. What I liked about it, Frank, was again, you know, I mean, I've seen many of these stamps, particularly those from Germany, but to hear about really the complicated physics and what underlies it and the theories, and yet very simple images on the stamp. So that was nice to be able to transition. But yeah, I enjoyed it very much. Thank you.
Good.
I have a question.
Please.
How many of the stamps that you showed today do you have in your personal collection?
Probably half a dozen. That's why I wanted that one stamp from you, Rex.
Yeah. Well, we'll talk again.
Rex has that Hungarian stamp with the physician wearing the dark glasses. I'll find it yet. I'm not worried about it. I just haven't spent much time looking for them yet.
All right. It's trading material for something you've got.
I understand.
Okay.
Does anyone else have any questions or inquiries or experiences that they'd like to share? Do we have any other topical? Tom, we have a chat that says, can we register for the class, Dr. Corwin, and get those 2 points?
Absolutely. I'd love to have you there.
Very cute.
I don't know. Are any of my students here? If my students are here, you get 2 points on the first exam for being part of this. I see some of my previous students.
Yes, and I see some friends in medical coats, so it's the right audience.
Okay.
I'm really floored by how many countries have these stamps celebrating the various medical imaging. It's really, I honestly, I didn't know Mesopotamia. Was it Mesopotamia?
Macedonia.
Macedonia. That was wild. And that old, that.
With the mammo machine. Yes.
With the mammo machine. And then the gentleman who, what did he had? He put the catheter up his own body?
Herr Frossmann, yes, and 29. So everyone was saying, this will kill the patient. We can't do it. But he decided, no, it's not going to. So he had to do it on himself. And he actually had arranged with his nurse that he was going to do it on her. But as I read the reports, he tied her down to the table, did it on himself, and then he untied her to help him finish up. Maybe it was a man. Perhaps it was a gentleman nurse.
Oh, gosh.
But he was going to do it on himself. And once he got it all the way into his heart, then they walked down to radiology to get that X-ray picture.
All the way to his heart. Oh.
And he proved he wasn't dead. So.
You do have a student, Dr. Corwin, that's identifying themselves on the call.
Great.
So that's great.
You'll have to tell me afterwards here.
Okay, I will.
I don't see the chats anywhere.
Well, I'll share them with you. There are societies just for medical philately, right?
Yes, there is. I'm a member of, oh my goodness, chemistry and physics on postage stamp study units. So that's not really medical, but it's at least physics. And I have not seen any on medical. There has to be. I just haven't seen them. Because I would look more specific for medical physics, because medical could be very, very broad.
Okay, medical physics.
Or diagnostic imaging or something.
So in our chat box, Dr. Corwin, unless Daniela would like to read it out, read yourself, hon.
Yeah, I would like to introduce myself. I'm actually from Austria, so and from Germany.
Danke.
So because you were asking about medical philately, I'm actually member of the medical philately in Germany, which we have an association there. And I just wanted for you, Mr. Corwin, maybe there was in Czech Republic last year, they issued a stamp of a physician who is called Jedlička. And he actually was the first one to introduce X-ray apparatus in Prague. And I found it very interesting when I read this story is that they had the first X-ray machines in Prague actually in a hotel as an attraction. So the guests of this hotel could go by and see their own skeleton. So maybe if you want to have such an issue in your
I will look that one up. Yes, the Czech Republic.
Yeah, Czech Republic 2019, Mr. Jedlička.
Jedlička. Okay, great. Thank you.
I put it down in the chat so that you can have it.
Okay, good.
I thought this was it would be a nice story. Having the guests in the hotel going by and see the skeleton.
What an attraction.
It takes it into another documentary shortly. Thank you. Yes.
You're welcome.
Thank you, Daniela. Danke.
Thanks.
Oh, you have a previous student on here, Dr. Corwin, as well.
Arij, yes, I saw her. Thanks, Arij.
So when did you start collecting these, Dr. Corwin?
The actual medical physics stamps? Really, yes. Just since I've started incorporating them into my lectures. So in the last year. I haven't been doing this for a zillion years like some of your presenters have.
Well, Dr. Strittmatter hadn't either, and he was the catalyst to get for this talk. So I think it's fantastic to see all of these images and that you're sharing philately and all of the semiotic messages that are being shared through these stamps around the world are fascinating.
Yes.
Well, I really appreciate your time. Oh, excuse me. We have a chat. There is a stamp by India from 1998 on 20th International Congress of Radiology. Were you aware of that, Dr. 1998 International Conference of Radiology out of India.
Okay, I'll look it up.
Fabulous, friends.
I have a large list of different stamps. I have to see if I have that one. Okay.
Thank you.
Thank you.
Well, thank you, Dr. Corwin, for presenting on Stamp Chat, and thank you for watching and listening and for participating. Today's Stamp Chat was sponsored by the American Philatelic Research Library. APS members can borrow materials and request Philatelic research support. Visit stamplibrary.org to learn more about the APRL. You can also subscribe to the Philatelic Literature Review, the library's quarterly journal. Your subscription helps fund the library and all of the services we provide our patrons. Contact the library directly by emailing library@stamps.org or call 814-933-3803. This and many other Stamp Chats are available on the APS YouTube channel. Please use the comment box below to leave your thoughts and responses, and we will get back with you. We'll see you on the next Stamp Chat. Until then, connect, collect, and visit stamps.org to become an APS member. Thanks, friends. Thank you so much, Dr. Corwin.
Thank you, Heidi.